Hello, I'm Chuck Sobey from Channel Science and the co-founder of Chiplet Summit. As we've been putting together the fourth annual Chiplet Summit, we've noticed an opportunity, and that's what we wanted to talk with you about today. We see that chiplets are reshaping the memory storage hierarchy, and there may be new opportunities for alternative memories. In particular, we'll talk about AI and the changing workloads and how that's affecting memory and storage and the memory storage hierarchy, and where we see a potential opportunity for alternative memories. And we'll finish with identifying some opportunities at the intersection of AI, chiplets, and alternative memories. So what are these different workloads? Well, traditional workloads in the enterprise are designed for transactions, for the cloud, for analytics, and for virtualization. These enterprise workload characteristics stress the infrastructure in particular ways. They stress the CPU, the network, and the storage. They rely less on memory bandwidth and end up waiting for storage to respond. AI workloads are fundamentally different. They involve deep learning training, large language model inference, retrieval augmented generation, specifically storage techniques for RAG, and vector databases, hardware that's custom designed to optimize for searching vector databases. The AI workload characteristics stress memory bandwidth. For example, you could have 10 terabyte per second per GPU access required, which is 50 to 200 times a DDR5 bandwidth. Accesses are gigabyte-sized tensors rather than kilobyte-sized requests. We tend to see more sequential access versus the random access of the web and the cloud. And we see these algorithms needing to exercise the entire memory storage hierarchy rather than just a limited tier. The model size grows faster than the memory can feed it. And so that's one of the gating factors and something to look out for. And the economics of the data center changes. You'll hear it referred to as a token factory, and that token factory generates revenue. Another big underlying change with AI workloads is the enterprise workloads were largely interacting with people. And the AI workloads will see more and more AI agents interacting with the AI infrastructure. And that means the speed and the scale is going to be like nothing we've ever seen before. And as that entire infrastructure changes, new opportunities will present themselves. I'm hoping to highlight those for you and see if those aren't places that you might be able to build your business for alternative memories. So how is the data center infrastructure responding to these changes in the workload? Many different ways. Every part of it needs to respond. First off, the I/O, which is networking and interconnects, we're seeing an emphasis on bandwidth instead of IOPS, input-output operations per second. They do this with high bandwidth fabrics. The emphasis is on feeding the GPU, feeding data to the GPU rather than the CPU. We're seeing examples like NVIDIA's NVLink to address that. The power requirements are enormous. Racks are being redesigned to be able to support an entire megawatt in a rack, 10 to 100 times what we've had in the past. So much power is used that the AI training and inference needs to be scheduled so it doesn't put a burden on the grid. And that's moving folks to on-site energy production, whether that's wind and solar or even nuclear. The security attack surfaces are different and expanded now. We always want confidential computing, but we also want a secure data pipeline to avoid poisoning the data set and model parameter tampering, which could have huge effects with just a few small model parameters changed. We also have renewed concern about isolating proprietary models and isolating proprietary data. As I already stated, the compute is around the GPU, and that's going to dominate the infrastructure decisions rather than the CPU, which is dominated for decades. We're going to see a a proliferation of AI accelerators that are targeted for different applications as well as for different algorithms to get down inside and accelerate the specific operations that those algorithms need and do so much more than we've ever seen in the past. And that may finally give us an opportunity to take advantage of all the ideas that have been around with processing in memory or processing near memory. In storage, the demands are different too. We've got training data, checkpoints, and vector stores. We have accessing tiers of storage for training and specific vector database hardware for retrieval augmented generation. In memory, high bandwidth memory is dominating HBM, and custom HBM are projected to continue that. CXL is enabling us to pool memory together. LPDDR is giving us low power alternatives to feed AI at the edge and in mobile devices. And all throughout there's chiplet opportunities. So in the coming slides, I'd like to focus briefly on power and memory and chiplets and bring those opportunities together. The electricity demands from the data center will look specifically at the US, where I'm based. In 2023, data centers consume 4.4% of the total US electricity. It's projected to consume 6.7 to 12% by 2028. And servers and hard disk drives are the largest consumers of energy in that. And we're expecting similar trends in other parts of the world. The AI data center is power limited and memory limited, not compute limited. And the models continue to grow, especially as AI helps us make new models. We're going to see this even quicker. And this simply compounds the AI demands in the data center. And so you know that the market has to respond to that. And memory and storage prices and demand are all up. And I've got a collection here of some recent headlines from DIGITIMES. Memory shortage hits 70% order fulfillment. Server DRAM prices surge 50%. HDD delivery delays extend to 2 years as QLC NAND capacity sells out early. Historic memory shortages across DRAM, NAND, SSD, and HDD. It's difficult to get memory and storage if you're not one of the largest companies. I think this can give emerging or alternative memory suppliers a unique opportunity to exploit, but they've got to do it now, and they've got to know how to manage that opportunity. So what do I mean by alternative memories? In a nutshell, anything that's not DRAM or flash, anything that doesn't have this multi-billion-dollar dedicated fabs just for them. So these are things like MRAM, RRAM, phase change memory, ferroelectric memory, and many other types of memory. It's been traditional to call them emerging memory, but things like MRAM and RRAM and PCM, they've been around so long, I prefer to call them alternative memories. And we've seen memories try to break into the DRAM and flash stronghold. At one time, DRAM was an upstart. Another time, flash was an upstart. Well, you want to make sure that you're solving a problem rather than just putting a marketing spin on it. And we've seen memories described as it's faster than flash and it's cheaper than DRAM, which sounds like a great option until you realize that you can look at that another way and say, well, gee, this memory is slower than DRAM and it's more expensive than flash. So just a clever marketing spin is not enough to bring your product to success. Just fitting in between DRAM and flash or some other, flash and SSD is really not enough. It's got to enable a new capability and provide, and that needs to be based on something that is differentiating about that memory. For example, MRAM is well known to be radiation tolerant, and other memories are known to be very good in high temperature environments. So you'd like to be able to capitalize on those opportunities. Another opportunity is if your new memory can replace an incumbent that has stopped scaling, and we'll take a look at that briefly soon as well. And memories can't be a static solution. They've got to continue to scale. You have to have a roadmap to higher capacity and lower cost, power, and latency. And wherever you can make a foothold, remember that there is a multi-billion-dollar industry in DRAM and one in flash that's continuing to make advances, lowering cost and increasing supply. You need to keep them always in view to see if they don't come and simply overcome your advantage with their incremental improvements. So an interesting story arrives with embedded memory, and thank my friend Jim Handy at Objective Analysis for sharing this image with me. He notes that on older process nodes, embedded SRAM was about the same size as logic on a chip. But because SRAM scaling became harder and harder in embedded applications as you got to higher and smaller and smaller process nodes, the logic continued to shrink, but the SRAM did not shrink at the same level. And so what you predominantly get is you're taking these very expensive high-end process nodes and only getting a little bit of the benefit from them because so much has to be devoted to SRAM. This is a wonderful opportunity for chiplets. So all of the CPUs, modern server CPUs and GPUs have chiplet-based architectures to more or less extent. And in a nutshell, chiplets disaggregate the functions from a traditional ASIC and break them up into smaller chiplets. And this was already predicted back in Gordon Moore's original paper where he laid out Moore's law. Some benefits you get of chiplets is they increase the yield. They allow larger areas to be used in the smallest process geometries for your most important functions like the logic for AI acceleration. You can optimize process node utilization by doing things like putting power in older, larger process nodes, I/O in different nodes, and of course, memory in different process nodes. And that allows you to bring your esoteric materials into that function without contaminating things like your high-end logic processes. These designs are in the inside the package level, and they increase the speed and decrease the power versus printed circuit board level systems. If they're done properly, they can increase or they can make you have faster time to market and give you the ability to reuse your designed, your chiplet in other systems. Doesn't come for free, of course. There's a lot of activity in advanced packaging to make this a reality. There's a need to have interoperability between chiplets, and there's challenges with testing these massive systems. I mentioned the memory hierarchy, and this is the traditional way that we deliver high-speed data to the processors through a series of tiers. You know, on the processor, it goes through some different levels of cache to fill the registers that work at the speed of the CPU or the GPU. Obviously, we can't have terabytes of that type of memory that close to the GPU or the CPU. So it's tiered out into the main memory and then into different more storage class tiers beyond that, all the way out to archiving. And I've got some graphics there for you that show where chiplet opportunities might be in that hierarchy. In general, we call the top of the pyramid the hot data and the bottom of the pyramid the cold data. So we have large capacity, slower access, and lower cost per terabyte at the bottom, and the fastest, most expensive, smallest memory at the top of the pyramid. In light of that idea of tiering, there's the question of when do you make data leave the cache that you have, these expensive caches, because it can't stay there forever. It was interesting to see that this very point was addressed recently at the Open Compute Project's Global Summit. And they reached back all the way, I think it was before 1986 even, for the first paper was about the 5-minute rule from Jim Gray. And that was, if your data is going to be accessed again in 10 minutes or less, keep it in DRAM. It's cheaper to leave it there. But if it's going to be longer than that, it's cheaper to go back to another tier of memory or storage and access it. AI has pushed this so fast now that 5-minute rule has become a 5-second rule. If you don't access it within 5 seconds, it should be ejected and some other more important data brought into that fast tier for hot data. So bringing these ideas together, I think there's a unique opportunity for people who have alternative memories to offer. And this is a topic that's certainly near to my heart, in addition to co-founding Chiplet Summit. I've been in the memory and storage industry for quite a number of years and have helped companies bring up emerging memories. And it offers a lot of challenges. And this right now is a unique opportunity. Take a look at your memory. Does it have an advantage in an embedded design? Run with that, but also determine if that can be brought over to a chiplet design that can then be reused in other designs to expand your market. There are growing applications and new and growing AI algorithms. Look at those from the inside and see if your technology, your memory technology, provides some unique advantage in that you can exploit and run with it. If the application that you're going after already lives in a chiplet ecosystem, typically there's platforms where there's interoperability that's been at a higher level of verification. Start there. A lot of people don't know where to start. If that's not the case, really jump in anywhere in any of these platforms, but be prepared for change. Realize that if you don't have IP or hardware in one of these ecosystems, one of these platforms, people can't design your technology in. They have to be able to access it. So start somewhere. And remember, never have a static offering with memory or storage. It's all about growing the capacity. So you've got to scale, and as you scale, you need to maintain the advantage that you've shown. If you can identify an opportunity in one niche, you can run with that. But if you have the opportunity to be a device that's reused, that's going to be even better. Aggressively pursue it. Areas to look at are the next wave of AI beyond agentic AI and reasoning AI is physical AI. So that's anything you can do to enhance the operation of robots. And then at the edge, whether it's glasses or phones or other IoT devices. And remember, DRAM and flash don't sleep. They are phenomenal in the advances that they're bringing. So always be aware of what they're offering to see if you can sustain your advantage over them as they continue to improve. So now's the time to make your move. DRAM and flash prices have risen sharply. Supplies of memory and storage are tight, and people are looking for alternatives. Look for leverage with that alternative memory chiplet that you've got. And remember, there are new metrics to look out for. What is the token per joule? How many tokens per joule can they achieve with your system? Tokens generate money. They make revenue for companies. They're trying to make token factories out of their data centers. And so tokens per second is another key metric. Memory and compute are foundations of AI. We may finally get to the point where processing in memory makes sense. Is your memory uniquely suited for some type of processing in memory? To be a long-term winner, you've got to sustain the advantage that you find after the price and supply eventually stabilize. They always do, and they always disrupt again too. But this ripple with AI is more than a ripple. It's a wave. And now is the time to take advantage of the unique opportunities in the industry. My recommendation to you is come visit us at Chiplet Summit. It's right around the corner, February 17 to 19 at the Santa Clara Convention Center in California. You'll see all the latest chiplet offerings, the different ecosystems, and you'll meet the top people in the industry. And if you need help, my company, Channel Science, will help you develop your chiplet strategy for memory, storage, or signal processing. Thank you very much.